Welcome to module number 6. In module number 6, we have come to a point where we've done a lot of work when we're attacking a system, maybe on the red team, maybe as a contractor, you are going for the hack on this system. So what have you done? Well, first of all, you or your team has done footprinting. And with footprinting, you've gone over the organization, the employees, the structure. We've looked up things in databases and so on to find out as much information as we can. The next phase would be to go into scanning. And we went into scanning, we used Nmap, we used other tools to both establish that there were live hosts on the network and then to pull down information about ports and protocols. Then from there, we took that port and protocol information and we enumerated it, banner grabbed, got information about the software that was running, versions of that software that were running. And then the next thing that we did is went into the area where we talked about vulnerabilities. And we found out there might be vulnerabilities. And maybe on your journey in this fictitious tale, you have discovered that there are dozens or scores or more vulnerabilities that you have found. And now we get to the point where it's time to exploit those vulnerabilities. And that is what brings us to system hacking. So let's have a look at it. System hacking is split into 4 different sections, but don't let that fool you. We have quite a lot of information to cover. We're going to start off in number 1, demonstrating the different password cracking and vulnerability exploitation techniques in order to gain access to that system. But gaining access to the system is not enough, because then we go to the second learning objective. And in this section, we're going to use privilege escalation techniques to get administrative privilege. Often this is called going for root. We want root access. We want administrative access so that we can do whatever we want on that system, leading us to be able to do whatever we want on the entire network. Next, we're going to go into learning objective number 3. We're going to try to hide the malicious activity and maintain remote access to the system. And then finally, we're going to hide evidence of compromise. It's going to take us in a wild ride of a lot of very fun areas, fun topics. We're going to zoom in closely. We're going to be looking at code. We're going to be looking at memory and many other items. Let's get started. Okay, so in our first learning objective, we are going to be concerned with cracking into a system, cracking passwords, taking those vulnerabilities that we found and taking advantage of them and running with them. And so let's have a look at some of the areas where we can crack into that system. The first one that we want to look at is SAM. SAM, what is SAM? SAM is a security system that you'll find on Windows workstations. And a lot of you work with computers all the time. And one of the things that I find is I get contacted by relatives and friends. And here's how it will often go. You know, I've had this laptop in the attic for a year, and now my daughter's going off to college and I can't remember the login. Can you crack it for me? If you ever did that, or if you ever want to do that, you're going to be cracking the SAM. Now, what the SAM is it's a password hash that is stored on the computer system. Let's have a look at it over here. So what we're looking at right here is pwdump 7. pwdump is a very nice little tool, and what you can do with it is you can go to where the SAM is stored and you can dump the hashes for the SAM. You see here we have an LM hash and an NTLM hash. Normally on a Windows 10 or 11 system, you're only going to get an NTLM hash. And then what you can do is use other tools to crack that hash, maybe using rainbow tables or other techniques that we'll look at in just a little while. We're going to see this tool on the far right, Minicats. That is an amazing tool to not only grab hashes, but to use it in a variety of attacks against Active Directory. That's what we'll be using that. And then Hashcat is great, disinternals. So there are a lot of tools. We'll be talking about many of them. So what we do with the SAM is the next thing we want to do is kind of understand how it works. And so what happens is we have an authentication process. It's called the NTLM authentication process. This process occurs when you have a peer-to-peer network. In other words, you're not using Active Directory. So when I want to establish a connection to a resource on the network, that resource and my workstation exchange that password hash. So if you look at it over here, what you see is we have the client computer and there's a hashing algorithm. We send back, and it says DC here, but an Active Directory domain controller, unless you really, really mess it up, is not going to be exchanging a hash. But either way, you finally gain access to the resource. What the domain controller is going to be doing instead of exchanging hashes, it's going to be using Kerberos. Kerberos is the major security tool in Active Directory, and it uses a system of ticket granting tickets and tickets. And I'm going to simplify Kerberos here. Essentially what happens is the client computer will send in a request for authentication. They'll be granted a ticket granting ticket and make use of that ticket granting ticket to get to a resource. In order to get to that resource, you have to be granted a ticket. So there's a difference between ticket granting tickets, and we'll explore that a little bit more as we get into hacking Active Directory. So with password cracking, there are many different ways to do it. Let's have a look over here at some of the methods for password cracking. One of them would be non-electronic attacks. So this is where we're going to be doing essentially social engineering. That is one of the best ways to get a password, but you can also look at it while someone's typing it. We have active online attacks. These are the most exciting, the ones you read about more often: dictionary, brute force attacks, hash injection. We'll talk about a lot of these. Passive online attacks, and we're just sniffing, or we're doing an MITM, a man in the middle. And then offline attacks is where we take the hashes and we offload them, and we use resources to crunch that or those materials that we have. So with an active online attack, we have the idea of a dictionary attack. Have you ever seen a password dictionary? So when you go online, you'll find that there are these dictionaries, and they can have millions, even tens of millions in some cases, of passwords. And we have passwords that have been cracked before. We have some of the most common passwords like password 123. If that's your password, you should change it. You'll find, if you look at some of these lists, that they are the names of football teams or something like that. So you have hundreds of thousands or millions of entries in these. And so what we do is we use these dictionaries to try over and over again with these passwords until we're able to break into there. So we have a dictionary attack, but we also have a brute force attack. Now this one is tough, because what happens is you take the password, you try every combination of that password. The longer it is, the longer it'll take to do it. My problem with this is, statistically, when you look at how long a brute force attack takes, you get to the age of the universe. And there you are, waiting for your brute force attack as all the stars turn into black holes, and eventually the universe gets sucked back in, and then you have to wait for another universe until your brute force attack is finished. And I usually, after a couple of million years, I'm usually tired of waiting. So joking aside, this doesn't do a very good job with long passwords. And what we have as a technology that's coming in the very near future is a high qubit quantum computers that will be able to do variants of the Shor algorithm to be able to help with brute force. But right now, yeah, that doesn't work very well. And then another one is a rule-based attack. With a rule-based attack, what happens is you know something about the password. Let's say that there's a company and it's company name dash the password. Company name dash password. So I already have half the password, or at least a good chunk of it, if I just put in the company name. All right, so now let's have a look at some of the steps that we use to perform these attacks. So let's head on over here and look first of all at the steps, and then we'll just zoom in a little bit and see how that looks when we do this. Also, you will find in the lab, we're going to be doing a lot of this work. First of all, we're going to obtain a word list. So very often what you'll need is one word list of usernames and another word list of passwords. And we're going to go pop that in the user share word list directory. And then we're going to create a customized dictionary of passwords. You want to tailor these as much as possible to the target. And then you're going to run these commands to generate that customized dictionary. And so this is the John. So John, that command, we're going to be using this in the lab, and we're going to be using it in another slide coming up. But it's John the Ripper. Give it the path to the word list. And then you run John the Ripper with the word list with the path to those word lists. And then you hit enter. And once you run John the Ripper, it'll churn through. And eventually, if the password is on that word list, what it will do is it will find the password and crack into it. So that is a dictionary, or actually this is a dictionary. This is not a brute force, but it works really well if you have a good word list. All right, so we have also active online attacks. This is a PTH, and we're going to see various variants of the PTH. So let's have a look here and see what's going on in the PTH here. So if you look at the user computer on the left, the first thing this user is going to do is log in, and they're going to have hashes in a SAM file. And then if you look at the hacker on the other side, the compromised server he has already compromised that server using some type of exploit. And then he injects hash into that. And now, because of that hash injection, he has access to anything that the user is doing. And so we'll see that there are many variants of this, and we'll get into that in just a few minutes. All right, so I want to talk to you about another variant of this. It's sort of similar, but in this case, what we're doing is we're grabbing the hash, and then we're using that to exploit the system. This is called an LMNR NBTNS poisoning attack. LMNR is link local multicast name resolution. What is LMNR? Well, what it is when you're on a Microsoft network, if you are trying to get to a folder, you need to know the machine name in order to get to that folder. So let's say it's called Workstation 5, or let's call it Server 5. It's on a server. And that name needs to be resolved. Now, I'm going to tell you the best way to resolve that name is not with LLMNR, with NetBIOS over TCP/IP, which is that NBTNS. Instead of doing that, you should just be using DNS. But that aside, if you're using this technique, then wow, it is very hackable, and the hacking is actually very fun. You'll see this in the lab. Let's go over here and have a look at what happens. So the first thing that you're going to do is you're going to go to your Parrot Security Linux box, and you're going to be using a responder. And with responder, you're going to specify the interface that connects to that network. And then once you do that, you hit enter, and it waits. Let's go to the other side over here. And what's going to happen while it's waiting to respond. And so let's say that there's a user, and the user wants to get to a resource on the network. So he types in whack whack server name. Whack whack. I'm not quacking like a duck. No, whack whack is //. Just how you say it in Microsoftese. //, and then the name of the computer. In this case, it says data server. Now, what's going to happen? You'll see this in the lab. Don't get fooled by it. I have so many students that when they see this, they stop working in the lab because it freaks them out. What happens is there's a pop-up that happens that says, I'm sorry, I can't get to that resource. But that is a fake response. Let's go over here and have a look at what actually happened. So responder sent that fake message saying that it can't get to the resource. Meanwhile, it captures the login hash. Once we capture the login hash, then we can go to John the Ripper and use that in order to crack into it. So anyway, that's how that one works. You'll see this in the lab. The next one we're going to look at is going to be using Kerberos cracking. So let's have a look at this slide here. And so what we're going to be doing here is called ASREP roasting attack. And what we're doing here is we are taking advantage of somebody who has misconfigured Active Directory, and they set the do not require, see that right there? Do not require Kerberos pre-authentication. If they did that, we're in trouble. So we can use a couple different tools here to extract the password hash of the computer because of that misconfiguration. But let's look a little bit further. What we see here is that they are looking at the Kerberos protocol, they're targeting Active Directory, and let's go over here to the slide here. We'll see that they are extracting the password hash from that TGT service. What are we using for this? We're using Rubios for this one. Rubios is actually pretty cool. And then we can use Hashcat and crack into that system. So a couple different tools that we use. I would say it's very easy to do, but it's only easy when that Active Directory is misconfigured, unfortunately. And this can happen. I've seen this with small businesses, medium-sized businesses. I really haven't seen it with large organizations, but what'll happen is you'll get a new network administrator that is not as familiar with Active Directory. And when you're setting up Active Directory, there are all these fine-tuning settings that you can do for your domain controllers. And some of them seem like they might be enticing. Like, well, maybe if I do this, it'll make Active Directory better. It won't, because the default settings are actually fairly good for Active Directory. The second thing that a lot of these attacks are going to be made possible because of is backward compatibility. Active Directory might be installed on a network, and there was a previous network or there were previous applications that required the settings of Active Directory to be fine-tuned, and in doing that, we make it more vulnerable. All right, so let's have a look at the next one. This is called a pass the ticket attack. And so this one, we're going to be using Mimikatz to pass the ticket. And so we're going to, if you see the little window at the bottom right-hand corner, you see that little circle? That's the Mimikatz emblem. We can use Rubios and other tools to do this. But what we're doing is we are creating a method whereby we can grab pin codes, Kerberos tickets, etc. And we'll see this a little bit later when we get into the lab. We're going to run one of the pass the ticket attacks in the lab. Also, we have NTLM relay. And anytime we're dealing with NTLM, one of the big problems is it's so hackable. And so it's very important where possible not to use NTLM. Remember, I was telling you in the previous module that NTLM means old. NTLM means hackable. So let's have a look at what we're doing with the NTLM relay attack. And so we are intercepting, as you see at the top line, and relaying the authentication request, giving us the ability to impersonate the actual person or the client or the computer that should be doing the communications. So if you look over here, we're doing something that we're seeing a little bit earlier. We're running responder, and we tell it to go to ETH0, and we're going to wait for somebody to try to get to a resource on the internet, on the network in this case, and then we capture the NTLM v2 hash. Now let's go over here to this side, and there is a very, very cool tool. This is called Impacket. And so Impacket will set up the relay. And as you notice, we're going to home attacker responder logs and getting that hash. And then we'll be able to dump the hashes of the targeted system. And then we can crack those hashes, maybe using John the Ripper. Like usual, there are a lot of tools, and each of the tools that we use for cracking systems has a variety of parameters and a huge array of methods for their use. So one of the areas that can be very helpful is when we're doing it with AI, because we can have the AI do the work for us. So let's go back to the board and have a look at what we're doing with a shell GPT over here. And so what we're doing is we're going to be using the shell. We're typing in SGPT, and we're doing use Hydra. So that's the tool we're specifying to perform an SSH brute force, an IP address 10.10.19, using, and this is where we specify our collection of usernames and passwords and the location where those word lists are. And then we run the attack. But there are other tools that we can use that don't even involve AI. And one of my favorites is Loftcrack. Have you ever heard of Loftcrack? Loftcrack has been around for a long time. And what happened is it was sort of open source for a while. And then for a while it was closed source. And now it's open source again. We're going to do a lab with Loftcrack in it also. You can find it, download it. It's free. Run it, crack things. There's Loftcrack. There's Brutus, BruteX. There's a secure shell brute forcer. And over here, we're just using Hydra to run that attack. So lots of different tools available for attacking passwords. And so let's have a look at one of the techniques that we can use to defend against that. So what happens with a lot of these tools is, let's say that there's a 7 or 8 character password. That is fairly easy to crack if you have a very good dictionary for those hashes. You want to crack those hashes. But if you want to defend a common or easy password, what you can do is you can just put some random stuff at the end of the hash so that it will not match any other hash. And that is called password salting. By the way, this is a look ahead into the class, because the very last topic I'm going to talk about in the entire class is password salting. It's called key stretching, making that even longer. So keep that in mind when we get towards the end. All right, so let's have a look at how to defend against password hacking. And I really think that most people in this class already know some of this stuff. So we'll do a quick overview. So let's have a look here. And if you look at number 1, ensure that you follow the best practices when setting a password. One of my favorite best practices is to use a passphrase. In fact, you can look this up. If you go to your browser, go to a search engine and do a look up of password entropy. And then the keyword that you need here is XKCD. So password ENTROPY, XKCD. And a lot of you are like, XKCD, I know that. That's the comic strip for nerds and geeks. It's really a cool little comic strip. So if you do that, what you'll see is there's like a 6-panel comic strip. The last panel says horse, battery, staple. And what they are showing in this one is that in order to make a password less crackable, you need a high entropy password, which essentially means that it needs to be a long phrase. But it doesn't have to be something that is so random that you can't remember it. You can make it something easy to remember, but very long. So a 20-character passphrase can be very easy to remember for humans, but extremely long in terms of the phase space that it would take to crack that password. So that's number 1. Number 2 is audit. Number 3, don't share your password. So for instance, I would never tell you that I use password 123 on all of my accounts. I'm not going to tell you that. All right. Next thing we look at is number 4. Don't use clear text. Use encryption. Number 5, set your policy to 30 days. So the password expires in 30 days. And this one is enable syskey, but I want to give you a warning about syskey. Syskey was, notice I'm talking about it in the past tense, was great, because what it would do is take that hash that you're using with the SAM, with that, large NTLM hash, and what it will do is it essentially sort of salts it. It protects it so you can't get to it. But it's another thing you can look up on a browser tab. Type in syskey scam. Syskey scam. There are scams, and scammers would use syskeys to take over people's systems. So you know what Microsoft did? They said, forget about it. You can't use this anymore. And they deprecated syskey, and instead they want you to use whole disk encryption. So you see what I'm talking about if you look up syskey scam. The next thing we look at is we're going to be monitoring logs. We're going to be making sure that we are careful that we find out where passwords are stored, make sure nothing's in clear text, do account lockout. So if they try 3 times to get locked out or something like that, and also geolock accounts. So in other words, if I take a device out of a certain area, it locks. All right, so now let's have a look at the next phase of this. And we're going to take the vulnerabilities that we found in the previous section, and we're going to exploit them. As you look at the slide, we see that there are 7 different areas that we're going to look at. Number 1 is we're going to identify the vulnerability. Number 2, the risk. Number 3, we're going to look at the capability, what it'll allow us to do. We're going to develop an exploit. And that word develop is actually pretty salient because sometimes you actually have to write your own code. We're not going to do that in this case, though. Number 5 is select a method. We might be able to do a remote or right there local on that system, generate, deliver the payload, and then we're going to gain remote access. All right, let's look at the first one. So you can also do this too. If you wanted, you could open up the Google Hacking Database. And then the Google Hacking Database, you go up to the little spider, the little bug on the left, and go into exploit, and then you can type in a search. Like for instance, let's say Linux. You type in Linux, and there are all these Linux exploits. You type in almost any app you can think of, and there are exploits against it. And each of them have it's very nice because you have the built-in code. And so you don't even have to build your own code for these exploits. It's all there already for you. And so the Google Hacking Database is a great place to start. And hopefully for your client or for your systems, none of your systems or apps or anything are listed on the Google Hacking Database. If they are, it's time to do a little bit of fixing. All right, so other tools that are very helpful in exploiting vulnerabilities. This is one, let's have a look at this slide here. This is one called WSNG, or the Windows Exploit Suggester, a very cool little Python-based tool that will actually go through and look at the network and suggest an exploit for you. It's actually pretty cool. Another one that we have is one that you've probably heard of before, and we've used it in the labs a little bit before. And this one is Metasploit. Now, let me back up a little bit and talk about Metasploit. Metasploit is a hacking tool that is useful for every phase of hacking. It is very flexible. It runs on Linux. It runs on Windows. But I will give you a warning. If you ever decide to install Metasploit on Windows, you need to dedicate the entire computer to Metasploit because it makes global changes that make that laptop almost unusable for anything else. So I like running it on Linux. We already have it on Parrot Security Linux, and it's very easy to use from there without having to install it. Other things about Metasploit. If you look at how it's set up, we have libraries, we have interfaces, we have modules. We can interface all kinds of security tools. We can write extensions to Metasploit. I often call Metasploit the baby universe of hacking. So we go into the exploit part of Metasploit. It's an exploit module where we can configure an exploit and verify. And in the lab, what we're going to actually do is you'll see that we can run through a verification, select the target, select the payload. And once we have all that stuff put together, we launch the exploit. There are also payload modules and auxiliary modules. This makes Metasploit extremely extensible, where we can establish comm channels, execute arbitrary code. And by the way, that term, arbitrary code, whenever you see that, that is a bonanza for an attacker. That means you can put whatever you want into that slot. So being able to execute arbitrary code is really cool. We also see here that in an aux module, we might be able to do more arbitrary sort of one-off hacks that also make Metasploit very, very helpful. There is another really cool module in Metasploit that I want to explore with you a little bit, and that is called the no-ops module. There's no-ops and an encoder module. So we have the idea of a no-ops sled. And as you see in that first bullet point, it says generates no operation instruction used for blocking out buffers. What in the world does that mean? Well, what we're doing with that is what we want to do is we want to pad or slide the execution flow that we are running into the shell code. And so we have these instructions that do nothing but advance the instruction pointer as we look at line by line of code, making it easier to land on the payload. So what we do with the no-ops module in Metasploit is generate what's called a no-ops sled of a specific size. And then that sled can be used to do padding, fill buffers for an exploit. And what we're trying to do with the no-ops sled is make what we are doing compatible with various operating systems, etc. And then when we have coder modules, what we do is we encode payloads. Again, we're trying to make it compatible under a variety of situations. With the encoder module, this helps you avoid antivirus detection, IDS detection. And so we have obfuscation that's available to hide the true nature of the exploit, bypassing signature detection, polymorphism, where each time the payload is generated, the encoder modifies the appearance of it just a little bit. What we're trying to do is avoid the likelihood of detection. We also have a couple of other modules we want to talk about with Metasploit. One is evasion and post-exploitation module. So evasion allows us to get around IDSs, IPSs, and endpoint protection. And post-exploitation is once we've compromised the system, then we can use these to gain further access into the system. All right, and now we look at some AI-powered tools. Nebula is a nice one to find vulnerabilities. Deep Exploit, another really good tool to find vulnerabilities and run exploits. And then we move into the idea of buffer overflow. Buffer overflow is one of the most useful techniques to do a variety of attacks on a system. So this section is going to get a little bit technical, but I'm going to slow down. We're going to talk about what it does. I also want to run an advertisement for you. And no, I don't want you to like and subscribe. What I want to advertise is the lab. So in the first lab for module 6, we have a very well-written buffer overflow lab. And you'll see that it's based upon this. So if you go through this and some of it is a little bit hazy or fuzzy, you want to go back and understand it, go through the lab and then go back through this module again. Let's have a look and see what we're going to be talking about in this section. First of all, what is a buffer? When you run a binary, so that's an executable, some type of program that runs, it requires two major items. Number one is CPU access. So your CPU is going to be running clock cycles, taking information off the bus and processing it, making use of its various caches, and eventually sending those commands and etc. around the MOBO, the motherboard, to execute whatever you want and software, etc. So the CPU. And where is that CPU going to be running that code from? RAM, random access memory. And so if right now you're looking at this on a computer, you may have other tabs open. I mean, I had you go over to XKCD, so you may have other apps open. All of that you see on that screen is running in RAM through your CPU. So let's have a look over here what the problem can be. When the app is written, it is allocated only a certain set of locations in RAM. If it goes beyond its allocated location, we have a buffer overflow. And a buffer overflows happen because if you look at all these bullet points down here, it was programmed bad. There we go. Just summarize it, right? They didn't do bounds checking. They had old versions of things. They had bad programming practices. If you look over here, improper memory allocation, insufficient sanitation. So they did a bad job. We have this thing called the CI/CD pipeline. The CI/CD pipeline has a constant delivery loop that we use to keep software current and fresh. And that needs to be paired with a DevSecOps operation that will make sure that every part of code that you deliver is secure. If you don't have that, then it's very likely you'll put out bad code. All right, so we're going to slow down and we're going to make our way through and talk about buffer overflow. All right, the first thing we want to talk about with buffer overflow is stack-based overflow. There are two major types we'll talk about is stack-based buffer overflow and heap-based buffer overflow. So with stack-based buffer overflow, we have, first of all, I want to show you how we put something on the stack. So this is a little piece of code written in C. And if you look at this, we have local variables and some function arguments. We have a stack function. We have a couple of variables, A and B, and we have values 10 and 20 that are passed into the stack function, and then those are pushed onto the stack when the function is called. And so when stack function is called, the space for those local variables and the function arguments are allocated on the stack. So we allocate that space. And then after the function returns, something very important, the space is freed and another process or application can make use of that space. So with a stack-based buffer overflow, this is going to happen when a program writes more data to the buffer that's located on the stack than what's actually allocated for that buffer. So what the stack is a contiguous space in memory that we use to organize data. What's this data? Well, it's associated with things like function calls, function parameters, local function variables, management information for that app. And so when a program writes more data to a buffer, little spot on that memory, it almost always is going to corrupt the adjacent data on the stack. And so if it was triggered by mistake, let's say that I'm running an app and there's a buffer overflow. Oops, hate when that happens. It can take that program and just crash it or make it operate incorrectly or, look weird or do something weird. A stack-based buffer overflow is a buffer overflow that can be triggered also. And so what we want to do is, in the case of attack, is cause that to happen in a way such that we can take control of that buffer space. One of the things you're going to see quite a lot in here is you're going to see a lot of different buffers like EIP, the extended stack pointer, and EBP, the extended base pointer, and EIP, extended instruction pointer. So you're going to see a lot of these as we go through and look at different types of buffer overflows. That's stack, right? So for stack, one other thing I didn't mention in the second bullet point is when you use a push operation, we store data on the stack. We use a pop operation to take data off the stack. A funny thing is, as I remember, back in the old days of the Commodore 64, do you remember? Did you ever? Yeah, some of you've had those before back in the old days. Very old computer. And the thing that got my young mind it just sounded so funny. It was called peek and poke to move information off and on the stack. All right, let's look at heap-based buffer overflow. And one of the things about heap that makes it different than stack is heap is dynamically allocated. And so what you'll see is we use a malloc to allocate it. So I have a little piece of code I want to show you here. It's hard to see this, but what we're doing with this is we have a malloc we're using to allocate memory on the heap, or allocating enough space in this little code snippet that I have here for 5 integers. It's an array that we're putting on there. And then we do a null check. We want to check to see if malloc returns a null, which would indicate that the memory allocation did not work. So we need to check for that. And then we store the data in multiples of 10 into this heap-based array. And then guess what we do when we're finished? Right at the bottom, in that section on the bottom of the code, we do memory deallocation. So after using that allocated memory, we free it, and it's called we deallocate it to prevent memory links. So this is, again, it's just using C programming. So let's talk about what happens when we overflow the heap. And so what we have here is, again, we see malloc used quite a lot here. And we can exploit a heap-based buffer overflow in various different manners. We corrupt the data in specific ways that cause the application to override its internal structures. Like, for instance, linked list pointers. That would be one of the ones that we do. So we have a canonical heap overflow technique that will also overwrite dynamic memory allocation linkage. In this case, we see as in malloc metadata. And so what happens is we overwrite the function pointer and we have a heap-based buffer overflow. So that's what we do, as you see in this slide, with heap-based. So stack-based and heap-based buffer overflows are the 2 places where we go. And I put up a couple pieces of code that were friendly. The code showed you how to basically put information onto the stack or put information onto the heap. And they run well and they work. The code you see over here doesn't work. All right, so if you look at this, what we see on the left is we do a stack-based overflow. So we're not putting information on the stack in order to demonstrate it. No, we are overflowing the stack. And if you look at the very bottom, you see that GCC right there. What we're doing with GCC is we are using a compiler to run the C code. And you'll see in both cases for stack and heap based that we overflow the buffer. And if you look at the heap based, you'll see, I like to say at the bottom, look at that, all those A's, it's going, I've been overflown, right? So that's what we're doing. Those two are code examples. Make sure that you have a good look at that, make a note of it, so that if you see a code sample appear on the exam or a practice exam, you look for some of the structures that you'll see in these to realize which one is stack and which one is heap. All right, so now what we're going to do is we're going to go over the steps for buffer overflow. And those are starting with performing spiking, moving into fuzzing, identifying the offset, overriding the EIP register, identifying bad characters, identify the right module, then we generate shellcode and gain root access. So let me just give you some advice right here. You need to know these steps. Let me give you an example exam question. Here we go. Exam question. Fred, who is a developer at XYZ CEH Corp, and he is testing his code to see if it's vulnerable to exploitation. Which of the following is not required for buffer overflow? So here's one. Ready? Generate shellcode. Perform fuzzing. Execute shellcode. Identify bad character. So execute shellcode is not on the list, right? It's not on the list. I mean, obviously you have to execute it, but it's not on the list. So therefore you would choose execute shellcode because it's not on that list. So make sure you know this list. And now what we're going to do is we're just about to go into step-by-step how to do this. The screen grabs that you see on here are taken from the lab itself. But before we do that, I want to talk a little bit about other techniques. There are other techniques for buffer overflow. We're going to look at some of them a little bit later, like heap spraying. And we already talked a little bit about using no-op sleds. And there are many techniques. But I tell you what, these steps that we have listed here are some of the best of the techniques in order to do buffer overflow. All right, let's get started. All right, the first thing we're going to be doing is we're going to do what is called spiking. So we're going to send these crafted TCP and UDP segments at the server that we have set up. So step one, we're going to establish a connection. I want you to see something very, very important here. We're using a really wonderful tool called Netcat. And what we're doing in the beginning, you'll see this when you run the lab with me, is this is called setting up a Netcat listener. And what it's doing is just going to wait there and listen. One of the most fun things that you get with a Netcat listener is when you are successful, in the end, it pops out a nice little prompt. It could be a prompt from Windows if you're doing a Windows exploit, or it could be a prompt from a Linux terminal if you're doing a terminal exploit. And then you can do a who am I, and you can find out, what level of access you had. That's really fun at the end of it. But meanwhile, it's going to sit there and wait for output from what you're doing on the other end. And then we're going to generate the spike templates and run the spiking. So what we're doing is we're throwing all kinds of data. There are two types of stress tests that we're going to run. The first one is spiking, and the next one is fuzzing. And so that's what we're doing here. We're running spiking. Now, I want you to also have a look at the app on the right. This is going to be our major tool that gives us insight at the byte level, the bit level, as to what's going on with the app itself. And if you look at the bottom right-hand corner, you'll see it says paused. Why? Because you blew it up. You spiked it so much that you overflowed one or more registers, and now the program stopped. We can go through here and look at the code. And we're going to do a little bit of an examination as to the output of Immunity Debugger as we get a little bit further in past fuzzing. So fuzzing, we use a nice little tool, little Python script called fuzzpy, and we run that. We send a huge amount of data. And in this case, what we're trying to do is extract the location of the EIP register. So before we go on, let me talk about overall what we're doing in the beginning. We have several different steps that we need to do to figure out where we are. Let me tell you why. All right. So I have a application. The application is running. It's going into allocated space, but where is that? What module is running? What function is running? if you look at how RAM is put together, it's like a city. It's like Los Angeles. And you have in some block in Los Angeles, everything went wrong, right? That is the buffer overflow. Where precisely is that located? We need to find that, right? The whole city of Los Angeles, which is now an app, crashed because of that one block. Right, let's find where that block is located, and let's find the entrance and exit to that. Let's characterize it so that we can run our own shell code in that area. So you have a lot of program to look at, and we're trying to characterize where in that program, where in RAM, what module that the buffer overflow takes place, so we can take advantage of that. So that's what we're doing with fuzzing and spiking, and we have a few more steps that we're going to use for this. All right, let's have a look at this one. What we're doing here is we're making use of the fuzzing. And I want to kind of zoom in on here and talk a little bit about what we're seeing here, because that is very helpful. What we're doing with this is we are looking at the disassembly window on the far left. So what we do is we took the app and we broke it down into all of its instructions and disassembled it, right? So this is the code. We have a server that we're running in the background called vulnserver.exe. And it has machine instructions that the CPU is running. And we have move, EAX, dword, PTR. There's a lot of different, this is actually, I think we highlighted that there. This is the current instruction that's being run by the CPU. And if you look at the top right-hand corner, that is the register window. And that gives us the current values of the CPU registers, like EIP, which is for your instruction pointers, like ESP, which is for your stack pointers, like EBP, which is for base pointers. And EIP really, in this case, is crucial because it indicates the next instruction that the CPU is going to execute. So in this case, what we're doing with fuzzing is we're trying to overwrite EIP to redirect code execution. Well, eventually we'll do that. What we want to do is run our malicious code there. Let's go to the bottom left-hand corner first. That's the hex dump. It shows the raw memory contents at the specific address where we are. We can see the data that was sent during fuzzing and how it's handled by the program. And you can also see ASCII characters like run complete. I don't know if you can see, that's kind of, you have to zoom in on it. And on MOHN. These are kind of artifacts of the fuzzing process. What it's doing is it's showing us that input data has been injected into memory. And then finally, at the bottom panel, we have the status bar, and it tells us that there was an access violation when reading 000, etc. E5, right? So it gives us a location. It attempted to read that memory, and it shouldn't have attempted to read that memory. This is because during fuzzing, we had malformed input that went into that caused a program to crash. And so what's this all about? Why would we do this? Well, because of that location in that module, it suggests that there's a potential vulnerability that we can exploit. All right, let's look at the next one. All right, so now if you look at this one, what we're doing is we're going to identify the offset. We're using a couple different modules, pattern create and pattern offset. What am I doing? What am I doing identifying the offset? So again, in Immunity Debugger, we see on the right-hand side that there's been a buffer overflow overriding the EIP in the vulnserver XE program. And we see random bytes are now in that register. They're random. So what we want to do is find the exact position. That exact position is the offset in the input where the buffer overflow happened. And that buffer overflow caused that EIP register to be overwritten. And so this is going to be crucial to have that exact location. So the first one we have is pattern create that you see in that little gray box at the upper left-hand corner. And this is actually a Ruby tool in Metasploit. So we're going to be using Metasploit. In fact, if you look at there's a big highlight on the far left-hand side there. That is Metasploit. We're using pattern create also. And so pattern create, what we're going to do is we're going to use this as a way to put input into that vulnerable program. And so it'll cause the program to crash, override the EIP. But what we want is to find the exact sequence of bytes. And then once we find that, we can use pattern offset to find the exact location. And if you look at the window on the right, you'll see that the terminal output says that an exact match was found at 2003. So on the 2003rd byte of the input pattern, that is where the buffer overflow starts to overwrite the EIP. And the reason this matters is because when we identify the offset as the attacker, we can then craft an exploit, and knowing the precise location, we can precisely control that EIP register and run our malicious shellcode. So that's what we're trying to do. We have to find out exactly where to do it. All right, let's have a look at this one where we are going to overwrite the EIP register with our malicious shellcode. So let's have a look here. We see that the EIP register, if you look at that number 42 that you see here, it's been successfully written by value 42424242, something like that. And that actually corresponds to ASCII B, the letter B, value 66, which is 0x42 in hexadecimal. So this is a very common technique that we use for buffer overflow exploitation. What we're trying to do is to test whether the attacker, in this case us, whether or not we have control over the EIP. And so we have a really nice script here for us at the far left side. That little window, the black window on the left, is a script called overwrite.py. It's a little Python script that's used to send something that we specifically craft into the vulnerable program, which in our lab is vulnserver.exe. And so the shellcode will have a variable that has 2003 in it, A characters to fill the buffer, and then followed by B characters. And those B characters are going to overwrite the EIP. So that's what we're doing in an immunity debugger on the far right. You can see this happened and it's paused, which means that it crashed. Bad characters. So what is this bad characters? It says that we need to identify bad characters. Well, let's talk about bad characters. They are specific values. They're byte values that can cause issues when we're running our shellcode. And so let's say we're running our shellcode and it discovers a character in there and it stops the shellcode from running. I'm not going to gain access to that system. So what I want to do is identify which characters are bad. So there could be anything that would like terminate the code or prematurely corrupt the way the code runs, make the code non-functional, stuff like that. So we need to identify those bad characters. And so an example, if you look at the bottom left-hand corner of the slide here, an example is that /x00, which is often used to identify the end of a string when you're programming in C. So what we're doing is we want to identify those. So when we inject into the EIP register, nothing will stop us from our attack, right? So we're going to be looking at byte values from x00 all the way to xff to find bad characters. So we're going to go through that, and you can see Immunity Debugger on the right-hand side has shown that, again, we cause it to stop. We have a value 414141, etc., which is a bunch of A's. And so what we have is raw memory, the contents of it, and we're able to identify anything that would stop our code from running, including bad characters. All right, so now that we know what might stop our shellcode from running, we need to know where exactly to run the shellcode. And so that's where we're going to get to the next step here, which is identifying the right module. So we want to have the correct module. And so very important to do, find that module within the target application that does not have things that might stop my code from running. Like for instance, DEP, data execution prevention, or ASLR, which is address space layout randomization. If I have a module that's protecting memory from my hack, that's not going to be very good for me. So we find the module with those protections, and then we can avoid them. So we're using a very good tool on the bottom right-hand corner called MonaPy, and it helps us to scan the module in that application and make sure we know exactly where the right module is. And then once the right module has been identified, then we can find a very good, or I guess you could say suitable instruction within that module to hijack the program's execution flow. So whenever we're doing a buffer overflow exploit, what we're going to look for is a JMP ESP. So JMP ESP instruction, that's what we're looking for. You can see this on the slide too, which can redirect the execution of our shellcode. So that's what we're really looking for. And then once we identify this location, we're ready for the exploit. All right, so let's have a look at this one. This is where we're going to try to take what we've found and extract that information. So we see there's a breakpoint that's been established, an address. If you look at, it's hard to see on this slide, but it's actually 0x, starts with a 26 and ends with an AF. You'll see this when you're in the lab. And there's a function that's in a dynamic link library called ESF function, func.dll. Either way, this is the address of a JMP ESP instruction or something like that that I could use to redirect the execution flow of my shell code. And then we highlight that. We have a nice little Python script we talked about before called jumpy, jump.py, that we use to exploit that vulnerability on the target computer. And so it's going to go to the offset of 2003, go to the appropriate address, and then we now have the ability to control the flow execution of the program. And so this is right towards the end of the buffer overflow process. We're almost ready to run the hack. All right, so now we go over to MSF Venom. And so with MSF Venom, this is where we're going to finish the attack. So we're using Metasploit, MSF Venom, love MSF Venom, and we use it for a lot of things in this class. You'll see that over and over again. And this is going to be where we generate the shellcode. It's a little payload that's going to be injected into the vulnerable application. What we're going to do with it is create what's called a reverse shell. And that way we can gain control of that system. And so if you look on the right side, you'll see that we have that reverse shell connecting to the machine. We have lhost equal to 10.10.113 and port 4444. That's 4 fours, right? That's what we're trying to do because we have a netcat listener already waiting for that. And then we take that generated shell code, we copy it and inject it into the target application, replacing the overwritten EIP register value with the address that points to the start of the shell code. And when the program execution reaches that specific point, then it'll execute the shell code, opening a reverse shell back to us, to the attacker. And then what'll happen, if you look at the bottom right-hand corner, this is the great part. The bottom right-hand corner, netcat listener then gives us that command prompt from that Windows system. And then from there, we can type in commands. The first command that you want to type in this situation is, who am I? And it tells you, you are an administrator. Nice. This means it happened. Now, we talked about quite a lot in that section. If there's stuff that you didn't understand, do the lab. And when you go over it a couple of times, it'll all make sense. All right, the next thing we want to talk about is ROP, a ROP attack. So what we're doing here is we're still talking about taking advantage of gaining access through low-level means. And this one is called oriented programming. That's what a ROP attack is. And it's a nice technique. It's a way to exploit, hijack a piece of code after you exploit a buffer overflow vulnerability. And so what you do is gain control of the call stack of the app, execute existing code snippets. They're already there. They already work within the program, within the shared libraries. And these code snippets that are already there are called gadgets. What is a gadget? It's a small sequence of instructions that usually end with, if you look at this, at the code on the right side, look at what it ends with, RET. See that RET? Or return instruction. So what happens is you could take these gadgets and chain them into your own attack. So they're supposed to run in a certain sequence, but you just change the sequence in which they run in order to run the attack. So you use a sequence of gadgets. And what you do is you create a new program, essentially. It's like taking Legos, right? Let's say the Legos are a boat and all the Legos are the gadgets. And then we rearrange those and then we have an airplane. So it's the same instructions, it's just in a different format now. So that is actually a pretty cool little methodology for attack. The next one we're going to look at is called heap spraying. So if you look at this slide over here, what you'll see is that we have a couple of different means of defending an app that I was talking about, ASLR and DEP. We want to bypass those. And so what we want to do is free space in memory with multiple copies of malicious code. So if you look at what we have here, we have before heap spraying, we have free space, we have allocated space. And now on the right side, we have an injected payload and we've taken up that free space. Very interesting stuff. So what DEP is data execution prevention. What ASLR is address, space, layout, randomization. And these help to protect apps. So what we're going to do is flood that free space and put in our own payload. And we have tools that can help out with that. All right, the next one we're looking at then is JIT spraying. And this is just in time. And so this is a technique where an attacker uses the just-in-time compiler. Where would you find a just-in-time compiler? Usually you're going to find that in a browser. And then what you're going to do is you're going to inject and then execute arbitrary code. Again, arbitrary code. Love those words as an attacker. And you're going to be able to run that. So the just-in-time compiler We'll translate that JavaScript that you've written for that app into machine code at runtime. And then we explain that process to put malicious code into memory. So number one, we trigger the compiler. And then number two, we do the memory allocation. And that helps us to bypass those security precautions that are there. And the reason it's so effective is because we're able to bypass security and because of the wide attack surface. It's time for AI. All right, so many different techniques, many different tools again. So now let's walk over here and talk about what we're doing using AI. So in this case, if you have used MSF Venom a few times before, you probably realize there are a lot of things you can do with MSF Venom and a lot of different variables that you can run with MSF Venom. You may not remember every single possible way to use MSF Venom, but guess what? Your AI does. And so you can say use MSF Venom to create a payload with host 10.10.113 and L port 444. Probably we mean 4444. No, we're doing just 3 4s in this case. And then from there, we have a look at this one where we say use the MSF console to start a listener with host 10.10.113 and port 444. So now we start a listener and it sets up that NCAT listener. And then once it sets up that listener, then we're able to proceed with the rest of the code. And we're not going to go into all the rest of the steps that we did before, but as you can see, we can use Shell GPT to make this happen. All right, so now it's time to get into a little bit more of Active Directory. And this takes us into the idea that admin tools are hacker tools. Over here on the slide, you see a very cool tool called Bloodhound. What you use Bloodhound to do is to characterize Active Directory. You can see it's got a nice little diagram here that shows how Active Directory is connected, what it's doing, and so on. And one of the things that it will do is identify vulnerable paths. So we can use Bloodhound on Active Directory to get that map and then find even for complex. In fact, Bloodhound is very good. One of the things that I've been able to do in terms of consulting and work is work with 2 major structures that are extremely complex. And one of those would be a university. And universities are crazy because you have all of these different colleges, and within the colleges, you have all these different areas, and everybody wants their own power. They want to control their own part of Active Directory. So you have to write special rules and so on, and it gets very, very complicated. The other one that I've worked with before is military bases. Again, they are very huge, and they have a variety of needs in terms of directory structure. Using something like Bloodhound helps somebody like me to make sure that I understand the flow of Active Directory and find areas where there are potential issues. But again, the attacker can use the same tool. All right, so now let's have another look at a tool. This one is actually another nice admin tool. Like I was saying, admin tools are hacker tools. What we're doing with this one called PowerView is making use of various Active Directory-based PowerShell commands to get more information on Active Directory. So we can, for instance, get domain policy or get properties from the domain, do some enumeration of Active Directory. It's a collection of tools that is extremely useful for characterizing Active Directory and hacking Active Directory. All right, next thing we look at then is a couple of other tools for AD enumeration. We're finding existing domain computers. Let's actually have a look at that. Let's go over here to the left-hand side here and look at some of these commands. If you're running Windows right now, you can right-click on the start icon on the bottom left-hand corner of your screen and go to PowerShell with admin, and then give the admin login, and then type in get-net computer. If you're connected on the network, it'll dump out information about the system. Over here, if you're on Active Directory, which I would imagine not all of you in this class would be, but you could do a get-net group, and it tells you the groups with which you are associated. And then I want to have a look at this one over here, where we're doing a get-net GPO. That's a group policy object. And then that vertical is a pipe. We're going to pipe that into a get object ACL and resolve GUIDs, the globally unique IDs, and then give it the specifics that we're looking for. And it takes all the GUIDs for those objects and lists them out for us. So these are just some basic examinations of how we can use PowerShell to find out information and enumerate the domain of a given network. All right, next we look at buffer overflow detection tools, because we don't want people like you or people like me running buffer overflow. So what we want to do is make sure that that is not possible. So a few tools that we look at over here, we have Veracode, Fault Finder, Q1, Splint. Over here is OllyDog. What these tools do is they look at your code, make sure that it's not vulnerable to a buffer overflow. We can also have a look at defending against buffer overflows. All right, I want to tell you a little bit here. This is one of the areas that, and there are going to be many of them in this class, that get deep into the dev side of things, the programming side of things. And so usually when we talk about items that are outside of operations, so for instance, I need to tell my developers to do, what I will do is overview these. So let's have a look at that over here. And so in operations, one of the things we can do is regularly patch. Oh yeah, okay. Perform code inspection manually. That's not something I can do in operations. This is what I'm going to say. Hey, dev team, I want you to do that and make sure that it meets certain criteria. Hey, what criteria? Well, let's go back and look at our DevSecOps. Let's look at how we secure our code, and that's going to be the criteria. Let's look over here at the left-hand side. And again, this is going to be fairly arbitrary depending on what your company does, but develop programs following secure coding practices. Again, that's fairly arbitrary. So here is what I want you to do. I want you to take all of these, and maybe this is going to be next year, and you're going to be working on a team. And I want you to refer back to these in your courseware and ask your dev team if they have that set up appropriately. But what you can do in the ops side of things is make sure that every aspect of that code environment has the latest patches and updates. So at least that environment is friendly to very good operating code. Okay, so we are in the second learning objective. In this case, what we're doing is we're going to be using different techniques to do privilege escalation and gain admin privileges. So let's have a look at this. All right, the first thing we're going to be looking at is the differences in privilege escalation. There are two types of privilege escalation. One is horizontal, and the other one is vertical. So let's look at horizontal first. So let's say that you find your way into a system and you only have a user account. And with a user account, you can't do much, but you're able to find another user account. Let's say this other user account is a DBA or DBO, which is a database administrator or a database owner. And maybe now I can hack through that database server since I've horizontally expanded my reach. But most privilege escalation is vertical privilege escalation. What they're looking to do is move from a user account to a root account or an admin account and move up, going for root. That is vertical privilege escalation. All right, so for privilege escalation, one of the methods for doing privilege escalations is to do DLL hijacking. So let's have a look at this. And while we're looking at it, I want to talk to you just a little bit about what a DLL is. A DLL stands for Dynamic Link Library. What is a dynamic link library? Well, it's a library that is dynamically linked. I'm just joking. I'll tell you what it is. Imagine that you're putting together a program, and this program has a horizontal scroll bar and a vertical scroll bar. Imagine also that this program has a file menu, and it has an edit menu and a help menu. And let's say that this is just one of dozens of apps that you're going to be working on throughout the year. Do you really want to put together the code for a horizontal scroll bar every time you create a new app and create a new set of code for the file menu, etc.? Rather, what you do is you have a dynamic link library. And so when it's time to use a horizontal scroll bar, you just reference hscroll or vscroll or f_menu or whatever, and you reference those in the library. And now I can write all those dozens or whatever pieces of code without having to rewrite all these. I just put them into a library and I put a call out to it. Okay, so what if I, as an attacker, can get a hold of that library, and when that app calls hscroll or whatever, it also is able to make use of my malicious code. So that's what we're talking about, privilege escalation using DLLs. There's a lot of other types of hacks we can do with DLLs. So well, the user installs an application, but the application, when it installs with the DLLs that the attacker already put in that library. And so something like Spartacus or PowerSploit can be used by an attacker in order to use a DLL to hijack the system. Right, so that's one of the things we can do. But there are quite a lot of other techniques to gain privilege escalation or to do privilege escalation. And one of the best places to find that is in the GHDB, the Google Hacking Database. So if you look at the Google Hacking Database and you go to that little spider in the upper left-hand corner and you do a little search, you might find privilege exploits that you might be able to run. All right, so let's have a look then at the next type of exploit. It's really the same thing, except for it's on a Mac and it's called a dilib instead of a DLL. Let's have a look at it. Same exact thing. We have a user, they're running an app. It's been the library, the dilibs have been exploited by an attacker. And so now malicious code can be used to gain privileged access through the Mac. All right. So the next thing we look at then is a couple of vulnerabilities called Spectre and Meltdown. So is it possible that your computer could be vulnerable to these vulnerabilities? The answer is yes, it is, period. That's it. Your computer is vulnerable. What it does is your CPU, let's say I'm a CPU. I'm a CPU and there's the bus to my right and every clock cycle, so let's say you have a CPU that's running at 1.5 gigahertz. So 1.5 billion times a second, I'm turning to the bus and I'm getting an instruction and I'm processing the instruction and then moving it on. Again, I turn to the bus, get an instruction, process it and move it on. But now I turn to the bus and I get an instruction and I'm like, oh, you know what? 7,283 instructions from now, there are going to be 5 instructions. They're going to tell me to do this. Whenever I see this instruction, 7,000 whatever instructions later, I get 5 instructions that I have to put together. So what I'm going to do is I'm going to take those 5 instructions and put them in a buffer and pre-stage them so that I can run them ahead. I'm doing what's called speculative execution. And what this does is one of the many tools that CPUs use to run faster. They know what's coming, they get ready for it, and they can run things even before they're told to do it. I don't care if it's an AMD. I don't care if it's an Intel. I don't care if it's an ARM. Your CPU is vulnerable to Spectre and Meltdown. So if you look at the Spectre one here on the left, let me get my laser pointer is working here. So they can read adjacent memory locations and get unauthorized access, read kernel memory, etc. Web-based attacks using JavaScript are possible with Spectre. And over here on Meltdown, they can get unprivileged access, forcing an unprivileged process to read adjacent memory. And they can get private keys and credentials, etc. So right now, virtually every computer has that. In fact, your computer is probably running slower right now because it's patched. So another type of privilege escalation that you can do is using named pipe impersonation. Let's have a look over here and talk about what's happening here. So what a named pipe is it's a way for a client-server LAN application to talk between the server and the client. And so if you can impersonate a different client, then you can gain privileges. So what we do is we have what would have been legitimate communications, but instead what we do is we use various tools, and these, by the way, are in Metasploit. And a lot of the tools that we'll be using for post-exploitation in Metasploit will be using get system for Windows. And so we use those tools in order to gain higher privileges. So there are many ways of doing this, and there are many different tools in Metasploit associated with that. So one of the things that we can do is make use of what are called unquoted service paths. And I want to say that in terms of services in general, there's a lot of potential low-hanging fruit to hack services because they can, in many cases, be misconfigured or they can be unprotected. So let's have a look here and see what we're doing with unquoted service paths. So if you look over here at the left here, that path to that service should be enclosed in quotation marks. And so what happens, it'll locate the binary through a specific path. But if it's unquoted, it'll make use of other means to find it. And the attacker can take advantage of that and insert their own code into that path. The next one, we have service object permissions. And so you can modify the attributes so much so with the service object that you can even create new users. If you look at another one, this is a very interesting one. I believe it was for Windows Vista. And so for Windows Vista, Microsoft did something really cool. Back in the old days, if I was working with an organization and I was working with the desktop support team, and the desktop support team needed to image a huge number of desktops. Or if I was working in the data center and I needed to image a huge number of servers, I would have to use something like Norton Ghost. And wow, we put together all kinds of really cool images with Norton Ghost. But as of Windows Vista, Microsoft started shipping Windows in the form of an image. And they provided us with imaging tools. And what did I say about tools for system administration? They're also hacker tools. So in this case, let's have a look over here and talk a little bit about this. When you use imaging tools, let's say I'm imaging different departments, different locations, and let's have a look over here and you'll see that I might be putting user information, password information, folder information into the settings of this file right here, onattend.xml. And very likely, your onattend.xml will be located in Windows System 32 sysprep. There's actually an app called sysprep that pops up and helps you work with imaging those systems. And so if I'm an attacker, that's another thing I'm going to be looking for. And maybe, just perhaps, I can find the information on admin accounts in the onattend.xml and then gain extra privileges. The next thing we look at then is pivoting. So